So for this presentation, we're going to be discussing geometries of molecules using balloons to demonstrate these different shapes. Throughout the presentation, it's going to be covering linear, triagonal planar, bent or angular, tetrahedral, trigonal pyramidal, and trigonal bipyramidal, and octahedral arrangements. The first and most basic one is the linear arrangement. For this one here, I'm using the example of CO2. It has two bonding areas, typically 0 lone pairs, and is linear in both its molecular geometry and electron domain geometry. That one looks like what I have on the screen. It is a simple two-part straight line through. It will also appear like this, so you have two straight balloons going across, and that will be all for that one. The next one is the triangular planar. It typically has 3 bonding areas and no lone pairs. This one here I'm using BF3 as an example. It is also triangular planar in its electron domain geometry as well as its molecular geometry. That one there, it is almost the same as the linear. You take the beginning and you basically are just adding another balloon in to make it like a 3 or a flat pyramid. After that, it's moving into the bent or angular example. That one there typically as well, 2 bonding areas, and the only difference between this and the previous one is that there is typically 1 or 2 lone pairs, which results in having that triangular formation again and the addition of a lone pair on the top, like I have in the image above. It is a good example is the HO2 or water. They have slightly different. It's got a tetrahedral electron domain geometry due to there being 4 areas of electron density where there's 2 bonds and 2 lone pairs, but the molecular geometry is bent, which is different from the previous. The tetrahedral has 4 bonding areas and no lone pairs. CH4 as an example, it is tetrahedral in the electron domain geometry as well as its molecular geometry. It is similar to some of the previous ones. You start off with 3 balloons or 3 pieces on the bottom, and you're basically taking the addition of a third on the top to make a pyramid. It's a little easier to see it in the image above, but I also have a kind of rotating model here so you can kind of see it in 3D. The next example following that is going to be the trigonal pyramidal. This has 3 bonding areas, and its only difference from the previous is it has an additional of a lone pair on the top. The example of this is NH3 or ammonia. Typically, it's tetrahedral in its electron domain geometry because of the 4 areas of electron density, and it's trigonal in its molecular geometry. Its difference from the previous is the addition of a lone pair on top, so just having a third into that rotation as from previous. Going to be trigonal bipyramidal. This one has 5 bonding areas and typically no lone pairs. PCl5 or phosphorus pentachloride is an example of a molecule that would have this arrangement. It's trigonal bipyramidal in its electron domain geometry as well as its molecular geometry. Typically, this one results with 4 in an arrangement on the bottom plus an additional on top. It would look kind of like this. A bit hard to see in the screen, but there is an image on the screen as well if that's helpful. The final one is an octahedral arrangement. This typically has 6 bonding areas and no lone pairs. SF6, or sulfur hexafluoride, is an example of a molecule that would be like that. It's got an octahedral electron domain geometry as well as its molecular geometry. That one there has, like I said, 6 bondings, so it is 6 combined into one. It is kind of a hard shape to take a picture of and kind of a hard one to show on the screen. I'm just going to slowly rotate it so you can kind of see it. It is a pretty big molecule shape. And then the screen here just has a table put together of all of the different types of geometry that can be found. They've got different examples of its molecules that would have a arrangement like that, as well as how many electron pairs and lone pairs would be found in each of those. And that's it.